So today we're going to look at infinite sequences and finite sequences. We found sums of a finite amount of numbers, meaning that we said we're going to find the sum of this many terms, and that was it. Now we're going to look at finding the sum of infinite geometric sequences, and just looking at geometric here. And then we're going to look at, writing fractions as, or repeating decimals as fractions. So infinite geometric series is one that goes on and on, keeps going on and on, that just continues. Convergent means is when the series kind of goes to a certain point. It's kind of like if you think of a touchdown, and if you were to a football field, and if we were to take half of the distance to the end zone and keep taking half, you would never actually go into the end zone, because you would, if you could possibly take half, you would be really close to that end zone, but you would never get that. So that would be a convergent series, because you are going to get really close to that line, the goal line, but not actually get into it. Where a divergent series continues and just keeps getting bigger and bigger and bigger and bigger, if there's not anything to change it. So here you see the graph of both. Here is an example of a convergent series. We see that it kept increasing until it got really close to 10, and then we're just kind of sitting right at 10 as we move along, and it just never really is going to cross that 10. It's just going to sit there at 10, so it's converging onto the number 10. Whereas here, this is getting bigger and bigger. My y's are getting bigger and bigger and bigger and bigger, and just keeps going. Here my x's continue, but they just keep getting bigger, and it's just going to keep going to infinity. So that is the example of both. Notice a convergent series, the absolute value of the ratio is less than 1, and a divergent, the absolute value of a ratio is greater than or equal to 1. So you can kind of tell without even seeing a graph which one it is. So here, if I wanted to see if this is convergent or divergent, I'd find my ratio. So take 243 divided by 729 to find my ratio. 729, and I get 1/3. And we see that the absolute value of 1/3 is 1/3, and it is less than 1. So this would be convergent. Here, if I take 5 divided by 2, I get 2.5. And that, the absolute value, is greater than 1. So this would be divergent. It's going to just keep going and going on to infinity, the values of it. This is just going to keep getting bigger and bigger and bigger. So I'll let you go ahead and look at those two on your own. If you have questions, make sure you ask. So to find the sum of an infinite geometric series, meaning we're going to add up every single term possible, we see we can only do this when it is convergent. So when the ratio is less than 1. If it is greater than 1, then the sum does not exist. So this is your formula. First term, 1 over r, if it is convergent. So here I'd take 4. Let's just go, since we don't, let's just divide these two. So negative 12 divided by 4 gives me negative 3, and that absolute value of that is greater than 1. So this is divergent, which means the sum does not exist. All right, here if I take negative 3 halves divided by 3, that would be -3/2 divided, or times 1/3, which equals -1/2. And the absolute value of that is 0.5, so that's less than 1. So this is convergent, which means the limit exists. So then we're going to go ahead and find that. Sorry, it's not spelling anything correctly. And that, again, is that A1 over 1 minus R. This formula here, A1 over 1 minus R. There we go. So then we would take our A1, which is 3, over 1 minus our R, which is -1/2. And that's important that we keep that negative. The absolute value was just to see that it's less than 1. So 3 over 1.5, or 3/2. And that's like 3 divided by 3/2, so it'd be the same as 3 times 2/3, which equals 2. So the sum is 2, and the reason that is because you can see we've got counting and subtracting, so it's we're almost taking away what we're putting in, and then also this is just getting closer and closer to 0. My numbers are on both sides of 0, so we're not really changing much. So that's our sum. So here, 4 divided by 2 is 2, so there's no sum. So my ratio is 2, so there's no sum. And this one, my ratio would exist, and you'll find, can go ahead and look at that sum. So when we put this into summation, like we did, it's going to look like this. And see, this is where it's really important that you understand the equation, like we talked about yesterday, because you can't really, there's not an infinity button on your calculator. So remember, this is our A1, or what I get when I plug in that 1, and that's my R. So we see that my R is 1/2, which is less than 1, so I can, this sum exists, and I can take, it would be A1 over 1 minus 1/2. So I would get 5 over 1/2, which would equal 10. So that is the sum of, that's that infinite sum. So next we're going to look at writing a decimal as a repeating fraction. So this, notice this line over top, we know that means that it's 0.25252525, and it keeps going. So we could write this as 1 over, or 25 over 100, because this is the 10th, 100th place, plus 25 tenth, the 100th, thousandths, 10 thousandths, plus, and then keep going on our repeated decimals. And that would keep going. So this is a sum. So to find my R, I'm going to take 25 over 10,000 divided by 25 over 100. So that would equal 25 over, should be 10,000, sorry, or 10,000 times 100 over 25. And the 25s cancel, zeros, and I get 1 over 100. So that's my ratio. So if I look at the sum of this, is going to be the same as this fraction as a decimal, or this decimal as a fraction. So A1 is 25 over 100 over 1 minus 1 over 100th. So 25 over 100 over 99/100th. We'll multiply by the reciprocal, 25 over 100, times 1 over 99. Hundreds cancel out, and I get 25 over 99. And you probably saw this, the algebraic method, in Algebra 1, but this would be one way we can use that to write those fractions in using our infinite geometric series. All right, if you have questions, make sure you ask. Thank you.